Welcome everyone, and today we are going to carry our discussion further and discuss the computation of critical flow. So in the last lecture we discussed the critical flow, the governing equation of critical flow, the concept of specific energy and specific force. So today we are going to understand, first thing will be estimating the section factor and hydraulic exponent for critical flow computation. The next learning objective, that is how the critical depth can be computed for various channel geometries. We've already seen the computation of uniform, that is a normal depth, and then we'll understand the concept of control sections. So what are control sections? So to begin with, we'll just quickly summarize the characteristics of a critical flow. So from the specific energy diagram, we have seen that the specific energy is minimum for a given discharge when there is a critical flow. Consequently, the discharge is maximum for a given specific energy. Also, the specific force is minimum for a given discharge. The velocity head, that is equal to half of the hydraulic depth in a channel of a small slope. The Froude number for critical flow is 1, and the velocity of flow in a channel of very small slope having a uniform velocity distribution, that is equal to the celerity of small waves in shallow water caused by the local disturbances. So basically your f is equal to 1, so v upon under root gy, that is equal to 1, so v is equal to root gy. So that is the last statement, that is the velocity of flow v, that is equal to root gy. Root gy, that the gy essentially term, that is a celerity of gravity waves. So the flow with which the velocity is happening, and the disturbances which are there in the waves in the flow, that are almost equal. So that can only happen when there is a critical flow. So in critical flow channel, the critical state of flow exists throughout the channel length or over a reach of a channel. So the critical flow criterion is known to you, that is q square t upon ga cube is equal to 1, and that can be simplified to achieve v square by 2g is d by 2. So that is the velocity as head is equal to half of the hydraulic depth. So we can see that the critical flow is a function of the geometric elements of a channel for a constant discharge. So this equation, if your q is kept constant, it depends upon t and a, which are nothing but the geometric elements. Okay, it can be a trapezoidal channel, you may have a y, b, m. It is a rectangular channel, you may have b and y. If it is a triangular channel, you may have m and y, and if it is a circular channel, you may have y and d. So these are the geometric elements on which d is the diameter on which it depends. Now, therefore, the critical depth in a channel of uniform slope will be same at all sections. So if you have a channel with a uniform slope, there is no change in the slope of the channel, you take different channel sections, your critical depth, let us say yc1, yc2, yc3, this all will be same at different directions. Okay, so here you have yc1, you have yc2, and so on. Here you have yc3. So these all three critical depths will be equal when your channel slope is uniform, so there is no change in the channel slope. That means your critical flow is independent of your slope, that is your s naught. It doesn't influence the yc and also the roughness. So if they are constant, your yc will not change. Now thus we can say that in case of a prismatic channel, the critical flow is a uniform flow because your critical depth is not changing. And what is the definition of uniform flow? The flow depth will not change. So for a prismatic channel, the critical flow will be uniform flow. Okay, now let us further understand the critical slope. So in case of Manning's equation, we have q is equal to 1 by n a r raised to 2 by 3 s naught raised to half. So when we consider the critical flow, your depth is critical depth. So in that context, the critical slope is the slope which will necessarily have a uniform flow for a given discharge where your flow depth is equal to the critical depth. So where your yn is equal to yc, under that condition whatever slope you get, that is your critical slope to sustain that given discharge. So the Manning's equation is modified as q is equal to 1 by n ac rc and sc raised to half. So ac is the flow area at critical depth, rc is the flow hydraulic radius at critical depth, and sc is your critical slope. So again, simplifying this equation, we have sc is equal to q square n square upon ac square r raised to 4 by 3. So your critical since your critical depth is a function of channel geometry and the discharge, your critical slope for a given channel section is a function of discharge only. So it again varies upon the discharge, your critical slope. So your critical slope will be a function of discharge, and based on the comparisons of your channel slope and critical slope, or based on your normal depth and critical depth, the channel slopes can be classified into three. So let us have a first comparison where S naught is your channel slope and SC is your critical slope. So three inequality exists. So let us say first case where S naught is less than SC. So in that case, your normal depth is greater than your critical depth. So what happens when normal depth is greater than critical depth? Your flow is subcritical, and such a channel where flow is subcritical is called as a mild slope channel. Okay, coming to the next case where your channel slope is greater than the critical slope, so your normal depth becomes less than the critical depth, and hence the flow becomes supercritical, that is Froude number is greater than 1, and such a channel is called a steep slope channel. In the last category, when SC is equal to S naught, so that means your Yn will be equal to Yc, flow will be critical, and that particular channel is called a critical slope channel. So thus the critical slope of a channel is a conceptual slope which depends on the discharge. So it is a conceptual slope which helps us to determine the nature of flow. Okay, it will give you an idea that what is a flow characteristic, whether it is a critical flow or a supercritical flow and all. So in previous class also we discussed about the specific energy concept. So there we discussed one point that the flow near the critical depth is unstable. So as we saw that in case of a supercritical flow, your velocity will be very high and depth will be low. In case of a subcritical flow, the depth will be high and velocity will be low. In case of a critical flow, your flow will appear to be unstable and wavy at critical state. Now why it is so? So the hint is, you can look at this specific energy diagram. This is your critical point. With respect to that, you will get the answer that why it happens that your flow at or near the critical depth is unstable. So why this criteria is very essential to cater. So if you, let us say, design a channel and you get yn is equal to yc, so should you proceed with that critical depth or you should discard it? So we should always try to avoid this in practice of adopting a depth near to the critical depth, because the flow is very unstable and it is wavy, and such conditions should be avoided, and we should go for conditions that gives us greater stability. So critical depth is unstable condition, we should avoid the channel design which is having a nearby critical depth. Okay, now next we move on to section factor for critical depth computation. So we've already seen the section factor for uniform flow computation. So based on the critical flow, we know that v square by 2g is equal to d by 2. So let us substitute q by a in this equation. So we get q square upon 2ga square, that is equal to d by 2. And on simplifying, we get, since your d is equal to a by t, so we get q square by g a square into a by t, and further simplifying we get q by root g, that is equal to a into a by root t, where this q by root g is called the section factor. Q by root g is called the section factor z. So this section factor is a function of your flow depth and the channel shape. So the two parameters that the section factor is dependent upon is the flow depth and the channel shape. So with this understanding, we'll further compute the hydraulic exponent for critical flow computation. Now, using the section factor as a function of flow depth, so it can be expressed as z square is equal to c y raised to m. Your m is your hydraulic exponent for your critical flow computation. Now let us take the logarithm of equation 5. So we get d by dy of ln z, that is m upon 2y. So we'll differentiate the equations on both sides with respect to y. So we get so I think this term d by dy will come here. So we get d by dy of ln z, that is 3 by 2a into dA by dy, that is minus. So look at the equation 4. So this is your equation 4, and we are now differentiating this equation 4 here. Okay, so equation 4, the LHS is dy of ln z, and the RHS is 3 by 2 into dA by dy minus 1 by 2t dt by dy. So after resubstitution and further solving, because you know dA by dy is t, so you get 3 by 2 t by a minus 1 by 2t dt by dA. So equation 7. So let us compare equation 6 and 7 because their LHS are same. So you get m upon 2y, that is equal to the RHS of equation 7, and on further simplification you arrive that m is equal to y upon a into 3t minus a by t dt by dy. So this is a general equation for hydraulic exponent m of for the critical flow computation. So we can see it is a function of the channel section because area and top width, and again a function of your flow depth. So it is not dependent upon discharge or any other parameter, the hydraulic exponent. Okay, so let us see how the hydraulic exponent can be computed for a rectangular section. Okay, so the cross section properties, you know, rectangular section area is b into y, top width is b, so section factor z is equal to a into under root a by t. So z square becomes a cube by t, so that is b cube y cube by b, and that is by cube. We also know that z square is equal to c into ym, so you equate equations a and b, and equating the powers of y, you get m is equal to 3. So in this graph, if you see the curves of m values, so in a trapezoidal section, if your side slope z is taken as 0, so it becomes a rectangular section, and for this it is a straight line, so that is m is equal to 3. For the trapezoidal section, for different channel slopes, you can see the variations. So your hydraulic exponent will vary between 3 to 5 for trapezoidal section. However, for circular section, we can see that within this depth, that is 0 to 0.8, close to 0.8, you can see the variation is very less for the hydraulic exponent. But once it crosses that depth and it nears the full depth or the diameter, you can see that indefinite changes in the hydraulic exponent happens at this particular range for a circular section. So when the depth of flow in a circular section approaches the top of the circle, the section factor and along with it the critical discharge would become indefinitely large because q by g is equal to g. So if section factor increases, the critical discharge would also increase and it becomes indefinitely large. So practically it will not be possible to maintain the critical flow in a circular conduit when your depth of flow is very close to the top of the section. Again, that which is our case that the water surface will be wavy where the critical flow is there near the top of the surface, and hence such conditions are undesirable when you design your channel section. Okay, let us understand the computation of critical depth. So as we derive for the uniform flow, the normal depth, here we can see, let us take a rectangular section. So the area is b into y and your top width is y. So we we will, since in that case we were going with the Manning's equation, here we'll go for the critical flow governing equation. Q square T upon GA cube is equal to 1. So Q by A is velocity. So we'll substitute this velocity, and then we are further making the changes that T is equal to B and area is B into YC. So you get VC square upon GYC is equal to 1, and further simplifying it, you get VC square by 2G is equal to YC by 2. That means the velocity head is equal to half of your critical depth for a rectangular section. Now let us evaluate the specific energy at critical depth. So specific energy EC is equal to YC plus VC square by 2G. VC square by 2G we have already derived here. So that is YC plus YC by 2. So EC is equal to 1.5 times the critical depth. So the specific energy at critical depth is 1.5 times the critical depth. So very important relationship. Similarly, if you want to derive the critical depth, so we know this relation Q square T upon GA cube is equal to 1 and Q is equal to Q by B. So when we simplify this, so what we get, that Q square upon G, that is equal to YC cube, and thus YC is equal to Q square by G raised to 1 by 3. So if you want to find out the critical depth for a rectangular section, you have to employ this equation and you will get the critical depth. And lastly, the Froude number V upon under root GY GD, where D is A by T and that is equal to Y. So Froude number is V upon under root GY. So that is the Froude number for your rectangular channel. Okay, now let us see for the triangular section. So the cross section properties for the triangular section, the area is equal to my square, where m is your side slope, and the top width is equal to 2my. So we'll substitute in this basic equation, and we get Q square upon G, that is equal to 2myc upon m cube yc raised to 6. So on simplifying, we get yc is equal to 2q square upon g m square the whole raised to 1 by 5. So yc for a triangular section can be found out using this relationship. So we'll now compute the specific energy. So EC is equal to YC plus VC square by 2. So V is equal to Q by A. So that becomes YC plus Q square upon 2G AC square. Now using this relationship, we will try to make some changes. So we have Q square upon 2 AC, 2G AC. So the remaining term we are taking on the RHS, that is AC by 2 TC, and we'll substitute the value. So that is myc square upon 4 myc, and this entire term becomes yc by 4. So the specific energy is equal to 1.25 times yc. What was in a rectangular channel, it was 1.5 times yc. So if the channel critical depth is same, the specific energy here will be lesser than what is obtained in case of a rectangular section. And similarly, the Froude number can also be calculated, and that comes out to be under root 2 V under root GY. So that is the Froude number in case of a triangular channel. Next, we'll try to approximate for a trapezoidal section. So for a trapezoidal section, that computations are not that straightforward. Okay, so area, that is b plus my into y, and top width is b plus 2my. So when we substitute, you get an equation of q square by g, that is equal to b plus myc into yc the whole cube upon b plus 2myc. So here you can see that it is a mixture of three components, b, m and y, c. So that means you have to adopt a trial and error approach to solve this equation, and then you will get the critical depth. Okay, similarly for Froude number also, it is a function of m, y and b for a given discharge, and again if you want to solve it, you have to go for this trial and error approach. Now going to the circular section, the geometrical properties are known to us, that is area is equal to d square by 8 2 theta minus sine 2 theta, and t is equal to d sine theta. So we again substitute and simplify it. So you get q upon under root g d raised to 5, that is equal to, now this fraction is 1 upon 1 upon 8 cube, and that is this fraction we are getting, into 2 theta c minus sine 2 theta c raised to 3 by 2 upon sine theta c raised to half. So this is straightforward simplification of this. So again we can see that this is a function of yc and d, and you apply a trial and error approach to get theta c, and then you can compute the other components using this relationship. So again, for a circular section, the Froude number is a function of y by d. So that means for a trapezoidal and circular section, the computation of critical depth is a complex task. Coming to the last part, that is control of flow or control section. So what does it means? So controlling flow literally means that you have some parameters. With the help of that, you can control the nature of flow, or you can more efficiently define the flow condition. So literally, if we talk, the control of flow means establishment of a definite flow condition in a channel, or a definite relationship must exist between the stage and discharge. So we already discussed what is stage and discharge while discussing the Manning's formula. So if we can have a definite relationship where a stage and corresponding discharge can be defined, that particular uh, condition is called control of flow. So when the control of flow is achieved at a certain channel section, the section is called a controlled section. So it is called a control section. So a control section usually restricts the flow such a way that the transmission effects or the changes in the flow conditions that happen either on the upstream or the downstream would depend upon the state of flow. So if any changes are happening in the flow, so let us say you have a sluice gate. With the help of sluice gate, if you lower or up raise the sluice gate, you can change the flow conditions. That is, if you lower the sluice gate, the downstream depth will decrease. If you raise the sluice gate, the downstream depth will increase, and correspondingly the upstream water level will also change. So that type of particular structure is called a control of flow, and a sluice gate can act as a control section because it is helpful in changing the flow conditions either upstream or downstream. So at a control section, if we look at the specific energy curve, we get two depths, that is the alternate depths for a given specific energy. But there comes one critical point at which your for a given discharge you have only one depth possible, and thus the critical stage of flow where you have a definite stage and discharge relationship is called a control section. So always wherever you find that the critical flow is established, that particular point is called a control section, and such a site is always suitable as a gauging site where you can measure the flow in a river and develop the discharge rating curve. So that is called a gauging site. So that brings us to a discussion question, that which of these sections can be established as a control section. I already gave you the hint. So which section is more suitable as a control section? So control section in a prismatic channel that is governed by the state of flow, that in turn is governed by the slope of channel, whether it is a mild slope channel, whether it is a steep slope channel, that we already discussed. So let us elaborate upon it. So in the first case, you have a mild slope channel. So in this channel on the downstream, you can see there is a long prismatic channel, and on the downstream there is a dam, and the flow is happening over the spillway. So due to construction of dam, there is a water is added. So there is a backwater curve you can see, and then the water is slowly going down. So that is called a drawdown curve. This dashed line indicates the critical depth. So what happens in a mild slope channel? Your S naught is less than SC, and thus your yn is greater than yc. So here Froude number is less than 1. So that is the case for a subcritical slope or mild slope channel. Now in case of a critical slope, you know that yn is equal to yc and Froude number is 1. And in case of a supercritical slope or a steep slope channel, you can see that the yn is less than yc and Froude number is greater than 1. Now what happens, we can also define these flow conditions based on the Froude number. So as we have seen that a Froude number, that is the ratio of the flow velocity, that is v, upon under root gy, that is the velocity with which the small disturbances can move in still water. So that we also saw in the starting. Now let us say in case of subcritical flow. Subcritical flow, what are the characteristics? The depth is large and the velocity is low. That is why the Froude number is less than 1. So when the Froude number is less than 1, any disturbance can travel upstream in such a flow. So what, any disturbance you make in the flow, it is able to travel upstream because your velocity is less. While in case of a supercritical flow, your velocity is high and stage is low, so any disturbance can only travel downstream, it cannot travel upstream because the velocity of flow is high compared to the velocity which with the disturbance can move in the still water. So in subcritical flow, the conditions are manifested such that the subcritical flow is affected only by the downstream conditions, while the supercritical flow is said to be affected by the upstream conditions and there is no role of the downstream conditions. So flow at the upstream condition can control the supercritical flow, while flow in the downstream, so the construction of dam can make the conditions in the upstream as subcritical, and in the critical there is no changes because both this flow velocity and velocity of the disturbance are equal, and that is why the section at which your flow is critical, that is called a control section. So based on this you can categorize that how your disturbances are traveling based on the flow conditions. Okay, so to summarize it, for subcritical slopes, change in water surface elevation downstream is transmitted upstream by a backwater curve, while in case of a supercritical slope, the effect cannot be transmitted for upstream, and that is why the controls differ. So with this we conclude, and two more discussion questions, that how controls of flow can be identified for subcritical and supercritical flows, and can you identify certain control sections? I discussed couple of them. Apart from that, any other control section you can visualize that can be discussed. So in the next class we will understand the applications of specific energy and critical depth concept in real world. So with this we complete our today's lecture, and we'll see you next time.